Hello and welcome back. In this video, we discuss about static equilibrium condition of a particle. Consider an object with a mass m held stationary with a force F as shown in the figure. Apart from force F, we have weight W and normal reaction N acting on this object to keep it in static equilibrium. In particle approximation, we assume the object to be a point mass or particle. The size or shape of the object is not considered. According to the Newton's first law, if an object is at rest, that is velocity is zero, or if it is moving with a constant velocity, that is motion along a straight line with a constant speed, then the net force acting on that object must be zero. This is called static equilibrium condition for that particle. We can write this mathematically as Fr, which is the resultant force acting on the object, is equal to the vector sum of the forces F, W, and N as equation 1. Consider a simple example. A 100 kilogram object is at rest, hanging on a cable as indicated. Draw the free body diagram of the weight, write down the condition for static equilibrium, and then find the tension T on the spring. The free body diagram of the weight shows two forces, tension T and weight W, acting on it as indicated. The condition for static equilibrium is that the net force Fr equals T plus W, vector T plus vector W, equal to 0, where T is the tension and W is the weight. We know that weight vector is 980 Newton acting in minus J direction. Therefore, the tension T is 980 Newton acting in the positive J direction. Another problem, a 250 kilogram engine is kept in static equilibrium using cables AB, AC, and AD as indicated. Calculate the tension in cables AB and AD. The first step is to analyze the static equilibrium condition of the engine. The free body diagram of the engine shows two forces, weight W and tension Tc. We know that the weight is 250 times 9.8 acting in the negative J direction. Therefore, the tension in the cable Tc will be 2450 Newton in the positive J direction. Now consider the free body diagram of the joint. The joint is under static equilibrium by tensions in the cables TD, TB, and TC. The condition for static equilibrium is that the net force acting on the joint is 0. We can now write the force vectors in terms of the magnitude and direction as shown in equation 4, 3, and 4. Note that the tension TD is acting in the negative I direction and tension TB has components in positive I and J directions. Using condition for static equilibrium, we can solve the unknowns. Equation 3 is the condition for static equilibrium for the joint. All forces are represented in terms of magnitude and directions. Grouping I and J components of this equation, we get equation 4. From equation 4, we get two scalar equations, 5 and 6, by equating the coefficients of basis vectors I and J to 0. These two equations have two unknowns, which is magnitude of TB and TD, which can be solved. Another problem, a block of mass 15 kg is resting on an inclined surface as shown in figure. Identify the forces acting on the block, draw free body diagrams, and write condition for static equilibrium. Also find the minimum value of coefficient of friction mu for this static condition. Note that in this problem, the reference coordinates are fixed on the inclined surface as indicated. Step 1 is to draw the free body diagram of the block. Weight is acting downward, normal reaction acts perpendicular to the plane, and frictional force is acting along the inclined surface opposing the motion. Once you identify the forces, we can write the condition for static equilibrium for the block, which is F resultant equals Fr plus W plus N must be 0. Step 3 is to express the force vectors in terms of basis vectors I and J and magnitudes of these forces. Here, the normal reaction N is in J direction. The weight components can be resolved into I and minus J direction. Frictional force acts in minus I direction. We can substitute these magnitudes and directions into the condition for static equilibrium. We get equation number 1. From equation 1, we can separate the I and J scalar equations and solve the unknown magnitude Fr and N. From this, we can calculate the coefficient of friction, because the coefficient of friction is the ratio of frictional force to the normal reaction. Another problem, object is under static equilibrium by 3 forces as indicated. Find the unknown vector F and its direction cosine. Follow step 1, 2, and 3 for the solution for this problem. However, for the force vector 3, the direction u is needed because only the magnitude is given. In order to find the unit vector along the direction of F3, we can use the position vector and its magnitude, because the position vector divided by the magnitude, you get the unit vector. Now you multiply the unit vector with the magnitude of F3, which is 700 Newton, you get the force vector. Finally, we can find the unknown force using the condition for static equilibrium. Once you have the unknown force F, we can find unknown force in terms of its basis vectors. We can find the direction cosines as we discussed in earlier videos.